Good afternoon, all. This video should be pretty short. This is the last topic in our transformations chapter. Woohoo! It's on symmetry. Symmetry is basically if you perform some type of transformation on an image and you get the same image, it's considered to have symmetry. It might have sounded a little confusing, but there's a few different types of symmetry. We have the first type, which is reflectional symmetry. We'll say it's A here. And with reflectional symmetry, this is essentially, again, reflectional, since we're talking about transformations, is like when you reflect over a line. So essentially, this is what you've known in the past as being your line symmetry. If a figure has line symmetry, that's essentially when you can draw a line through the figure so that it folds across that line. It would be a mirror image, etc. So I put a few letters of the alphabet here that have line symmetry, just to draw it in for you, just so you could see what this idea of line symmetry is. So if we looked at this letter, vertical line here, and again, if we folded across this vertical line, this would be the same figure, a mirror image. So this would be considered line symmetry. If a figure has line symmetry, you would be expected to draw all lines of symmetry on the figure. You wouldn't have to write it in words. You would just draw them on the figure, and that would be sufficient as to answering the question. Let me do that one a little neater. But that would be answering the question in regards to it having symmetry. If you didn't draw any lines, then basically it would be assumed that there was no line symmetry. With something like the letter O, this has an infinite number. Basically, it's a circle, but the letter O has an infinite number of lines that you could draw through it. So obviously, you couldn't draw them all. So for something like O, or if you just had a plain circle, you would just write infinite lines, because it could again be an infinite number of lines going on forever and ever. For this next figure, our stop sign, our octagon here, now if the word, I did it without the word stop because I didn't want you guys to think that, because obviously if stop was there, you can't technically draw any lines through it because it wouldn't have the reflection. But if we're just looking at essentially the octagon part of it, it does have line symmetry. We have a line coming down here. So I didn't put my line back. We could do this vertical line. We have a horizontal line. Now, a lot of people would stop with that, but there are additional lines. We can also draw across here, and we can draw across here. And all of those would be lines of symmetry for this octagon. All right. For the next figure, this is, to some degree, you can think of it as being a triangle. Obviously, it's not a triangle, but for this shape, we could draw a line of symmetry going through like the points kind of on each element here, and make it all our different lines of symmetry. All right, so let me move on. We have a few more pictures here just to show you some other ones. For the rectangle, this has vertical line symmetry. Sorry, that's not the best vertical line. But it does have vertical line symmetry. That could, it's like the same placement. I don't know why I feel like I'm a little off to the right. All right, let's try it again. All right, still not the best, but it's still better. So this would be pretty much how our two lines of symmetry would look. Often with the rectangle, students think that it has a diagonal line of symmetry. That is incorrect. The best way to explain that would be, normally I would just tell students to just take your notebook paper and just try to fold it. Like if you fold that across the middle, you'll see right there that it doesn't work. It's not going to line up, etc. But again, a lot of the time students do think that that diagonal line will work. For a rectangle. It will not. It's only going to be the horizontal and the vertical line. For the parallelogram, put this here just so, again, a lot of students will think that this will work. If you fold it, it'll end up being more like over here. it will not work. So I just wanted this one to be here as a none. So there's none here. For the square, now the square, because all sides are congruent here, this does have vertical, horizontal, pretend those look vertical, horizontal, and you can go on the diagonal with the square. So all of these would work. For the pentagon, basically you could go through any of these vertices and get a line of symmetry. So if you went through this one here, it will work. This one here would work because you could like fold over that line. Through this one here would work. Some of my lines are a little off, but basically any of these vertices, and this is if it's a regular, any of these like regular polygons would have, it would work that way where you could like kind of go through the vertices to make it work or whatever the case may be. Same thing here. I don't think I did it for my octagon up top actually. So you can go through the in-betweens. It's a little crooked. So you can go through like the mid, like to some degree you can call like the midpoint of the sides. So you can go through all of those, and you can also go through the vertices. Ooh, it's crooked. And you can also go through the vertices. And I didn't do that for the octagon. Let me do those as well, just so I have all the lines drawn. So for the octagon, in addition to going through like, technically these are the ones like going through the midpoints. You can also go through the vertices and have your lines of symmetry as well. So like any of these would work, going through the vertices or the midpoint situation would work if they're regular polygons. All right, so let's move on. So the next type of symmetry is rotational symmetry. When it comes to rotational symmetry, rotational symmetry exists if a figure can be rotated less than 180 degrees and map onto itself. Then it has rotational symmetry. So what this means is the following. So first thing, let me just tell you how you're going to find the degree, because that's going to be important, because rotational symmetry, you're always going to be asked for the degree. To find the degree of rotational symmetry, you're going to do 360, because that's the full circle, divided by, I'm going to put the number of elements. That might sound a little wonky, but I don't want to say the number of sides, because depending on how the shape looks, it's not necessarily size, etc. But it's going to be divided by the number of elements. So, excuse me. Sometimes that's the number of sides. Like for instance, if we look at this car symbol, counted the sides. It's 1, 2, 3. You know, it's all of these like weird things. What we're talking about is all of these like key elements. Like on this one, sorry, it's not erasing. So on this one, this is one element. This is like those congruent parts, or those equal sections, so to speak. So it's 1, 2, 3 points of interest, elements, etc. Again, how you word it doesn't matter. It's just understanding the concept. So if you take 360 and you divide it by 3, you're going to get 120. So if you rotate it from, let's just give it a name, A, B, C. If we're going from A to B, it's going to be 120 degrees. So we would have to rotate this 120 degrees for it to go back to mapping onto itself. And then from B to C would be 120, etc., 120. But, excuse me, so to get the credit for stating whether something has rotational symmetry, you're also going to have to know the degree. So again, it's going to be 360 divided by the number of elements. And in this case, it will be 120. If we're looking at this letter X, there's not too many letters of the alphabet that have rotational symmetry. For the letter X, it does, and only the lowercase x. If you look at the capital X, the space here is not the same as the space here. So I would say our capital X does not have rotational symmetry, but if we looked at the lowercase x, I'll give you that, because all of these, excuse me, all of the sections look a little bit more congruent. Like on this one, it doesn't, but normally when we draw x's, it looks pretty much equal all around. So I'll accept X as one of the letters of the alphabet that has it, but a lowercase x. And in that case, again, we're kind of looking at these elements. So it's 1, 2, 3, 4. So it would be 360 divided by 4. It doesn't look like 90, but rock with it. So we'll say this is 90 degrees rotational symmetry. Even though, again, it doesn't really look like it. But again, my x's tend to look a little bit more symmetrical than the typed ones do. Excuse me. When it comes to letter O, no matter what, it doesn't have, because it's the same. Again, this O looks a little off, but like I say, our regular O, it just looks like a circle. But this one does look like it's bigger this way than this way. But again, let's just say our letter O is a regular circle. So if it's a regular circle that we're thinking about, etc., it does have rotational symmetry. And because it's the same thing, it's just a circle, it could be any degree. You could just say 1 degree because, excuse me, any degree it moves around, it would have rotational symmetry. So if it's a circle, any degree would work. Rotational symmetry, and you could put any degree. All right. For the next one, for this octagon, so again, this one looks more like a stop sign, but it's all equal here. So basically, you're going to divide it by, in this case, we're going to do like the number of vertices, critical points, elements, however you want to think about it. So it's going to be 360 divided by 8, because there's 8 vertices here. When we do 360 divided by 8, we get 45 degrees. So this octagon has rotational symmetry of 45 degrees. If we went, again, I'm just going to give you a point to name it by. To go from A to B, it would be 45 degrees. And we would keep, anytime you rotated 45 degrees, it would map back onto itself. For this next one, for the square, this is, again, a square. And again, if it's a regular polygon, so we're talking regular, not anything where all the sides aren't equal. We're saying that these are all regular, all sides are equal. So if it's a regular polygon, like this square here, all sides are equal, we'll do 360 divided by 4, and it's going to be 90-degree rotational symmetry. All right, here are a few others. For the pentagon here, again, any of these, as long as they appear regular, they are regular. I'm not going to try to confuse you guys and throw in something that's slightly off. So this is a regular pentagon. So as long as it's regular, it's 1, 2, 3, 4, 5 elements we need to worry about are points. So it's going to be 360 divided by 5, which is going to be 72 degrees rotational symmetry. So again, to get from A to B, it will be 72 degrees. The next one here is a hexagon, 6 points. So 360 divided by 6, 60-degree rotational symmetry. Our next one here has 1, 4, 8, 9, 10 sides, or 10 vertices, 10 sides. So we're going to do 360 divided by 10, which means 36 degrees. That looks like 360. 36 degrees rotational symmetry. And for this last one, again, I just wanted to throw in something that doesn't look like a straight, it doesn't have to be, again, it doesn't have to be a regular polygon to work. If we look here, all of these are congruent, these little segments here. Excuse me. So it does have rotational symmetry. And this is what I meant again by sides. It's not necessarily we're looking at these little sides. We want to look at these key points. 1, 2, 3, 4, 5, 6, 7, 8 of those. So again, we would do 360 divided by 8, 45 degrees. So it would be 45 degrees to go from here to the next one. So 45-degree rotational symmetry. All right. And the last type of symmetry is point symmetry. Point symmetry is when you can rotate a figure exactly 180 degrees and map it onto itself. What point symmetry is it's basically if you turn a figure upside down, if you turn it upside down and it's the same thing, that, excuse me, essentially what it means to have point symmetry. Exactly 180 degrees is when you are backwards, you're turning backwards. So if it's 180, then it's considered to have point symmetry. All right, this is our third and final type of symmetry. So I put a few letters of the alphabet here that have point symmetry. Here's letter I. If we turned it directly upside down, it does have point symmetry. So you would basically just write point symmetry. You don't have to, draw any arrows or anything like that. You could put the point. It has point symmetry here. You can turn it upside down. It's the same O. Capital H has point symmetry. N has point symmetry. If we turned it upside down, it's the same thing. Our letter S here has point symmetry. And our letter X, if we did that, again, turned it upside down, has point symmetry. So all of these letters of the alphabet have point symmetry. I put one or two things on the side here that did not have point symmetry. So the heart here, no point symmetry. Again, if we turned it upside down, don't judge my drawing. I don't know how this is going to come out upside down or whatever. But it does not have point symmetry. For the next one, the face, again, if it was upside down, the eyes, the mouth would be reversed. So that does not have point symmetry. All right, let me move it up a bit. And here are the last few diagrams I have at the bottom, just to, again, show you some things that have points and things that don't have point. All right, so if we look at the hexagon here, first, it is not a given that every single regular polygon has point symmetry. In order to have point symmetry, again, the degree of rotation is going to have to be a multiple that goes into 180 evenly. So it would be upside down or exact at that point, and that isn't always going to happen. But for the hexagon, if we did 360 divided by 6, that would give us 60. And 60 is a factor of 180. So that means if we turn this upside down, point symmetry will work because the rotation is a factor of 180. So this is yes, point symmetry. For the rectangle, pretty sure you guys know that was obvious. If we turn the rectangle upside down, it's the same. So this is yes for point symmetry. For the next one, the parallelogram. This one would also work, even though these are different here. If we rotate it 180, it would end up being the same. So yes, point symmetry. For the octagon with the 8 sides, again, technically we would figure out the degree. We already figured it out earlier. It was 45 degrees by doing 360 divided by 8. And if we did 180 divided by 45, it does work. It goes in. So yes for point symmetry. Again, most of the point symmetries you can just tell visually. You don't have to show any math for it. It's pretty much a yes, no. For the last one here with the car symbol, for this one, if we looked at it, again, you should be able to tell. If we turn this upside down, I'm just going to go on the idea of it being a triangle. If we turn this upside down, it's going to look like this, which is obviously not the same as what it is here, pointing upward. So it's already a no, but to go and figure out, the exact reasoning with the degree, let me show you what that would be. So we already did 360 divided by 3, and got the answer of 120. So from here to there is 120 degrees. So if I did 180 divided by 120, it does not go in evenly. So therefore, that's why it's no point symmetry. All right, and I don't want you guys to think that these these x's here are meant to be line symmetry. All right, so that is it on symmetry. I'm post a few examples, some practice, and I'll post the answer keys. Have a great day.